How small can you make machinery? Okay, that's the subject. And because I've heard people around in the bath saying, tiny machines. What is he talking about, tiny machines? And I say to him, you know, very small machines, and it doesn't work. I am talking about very small machines, okay? Now, but before I start on machines, I'd like to talk about very small writing first. Okay, how small can we make writing? Or say numbers. How big does a number have to be? If you want to write numbers down, what's the smallest you could possibly make them? I don't mean how high, if you're very delicate with your finger, how small you can make them, but with special machinery and so on, what is the ultimate limit? Well, the ultimate limit is that you can't make a number. Of course, the number is just as good if you write it bigger or smaller. You say any size, but you can't make it smaller than atoms. You can't write on an atom. You can't mark the atom number 1. Because marks, you see, are just more atoms spread over other atoms, black atoms on top of white ones or whatever. So the way that you have to do to write something would be, let's say, to have a little patch of gold followed by a little patch of silver, by another silver, by a gold, and so on, and some sort of code like dots and dashes to represent numbers. And you could say that the smallest we could go would be, say, perhaps 100 atoms. Probably you can go down to 1 atom, but if you want to make it nice, 100 atoms on a side. And I'd like to talk about how small that really is, because you don't quite appreciate how much you could write if you could write that way. So I start out further back and talk about things that have done in the past. People have pointed out to me that the Lord's Prayer has been written on the head of a pin. All right, now let's see what we would have to do if we wanted to write the entire Encyclopedia Britannica on the head of a pin. Can we do that? Well, first of all, the Encyclopedia Britannica has something 20, 30, some odd thousand pages. And you imagine that each page is on a special piece of paper, and you put them all over the ground, and you get a great big area, you know, 20,000 square feet. And that has to be shrunk down to the size of a head of a pin. And after a little figuring, you'll figure it out yourself. It's about 20,000 times reduced. So if we could reduce the size of the words, the letters, the dots in the pictures, the whole thing, everything that's in the encyclopedia, only by 20,000 times this way, and of course this way too, so it's 40 million times difference in area. There's a lot of difference in area between the head of a pin and 20,000 square feet. Then we could write the entire encyclopedia on the head of a pin. And as I will indicate soon, that's not too difficult. To give you some idea of the scale in which to which that corresponds, an entire library, like the Caltech Scientific Library, can all be put on one library card. We could send all the information that's in the library on one library card, say to Brazil. If the scientific library in Brazil burns out, then we just send them a one library card which contains all the information in all the books in the Caltech library. The Congressional Library of Washington is larger and requires something like Time magazine to carry all that information at the scale. And so we see that if we could go down to 20,000 times smaller, and I'll tell you in a moment right away that that's nowhere near limits of atoms. They're not coming in at all at that scale. There's no problem in going 20,000 times, and that's the kind of scale that would be possible. So, just a moment while I look at my notes. If we made it in the three-dimensional manner, you see, all that I've done so far is writing on the flat of the pin. I haven't used the guts of the head of the pin. The Encyclopedia Britannica actually uses a volume. It has page after page. if we could write deeper, you see, not just on the surface of the pin, but in the interior, we could ask ourselves, let's do it with the atoms. That's much further reduced to get 5 atoms on a side, little cubes, that's 100 atoms of gold and silver and so on. And now I'm not doing the pictures, but I'm just putting all the words in some kind of code, like Morse code with dots and dashes, gold and silver. How much could we put into what space? All right, now it turns out if you take all the books in all the libraries, Turkish, Hungarian, everything, all over the entire world, and just take the information, because I can't get the pictures at this scale, then all this goes into a volume of material 1/200th of an inch on a side, which is the smallest piece of dust that you can possibly see. That's the net result of all mankind's arrangement of information. But all that information could be remembered in a piece of dust that size. And that gives us some idea about the fact that there's plenty of room to make things very much smaller than we ever made them before. Our books are obviously too big. What's the sense of having all that stuff in this big library when you can put it all in one card? Oh, it's convenient to have the books in your hand, but for some kind of a summary of all the information and to transmit the information from one place to the other, or send it, or suppose that you're afraid that all of civilization is going to collapse, and you would like to leave copies of the libraries, because you say everything in the Alexandria library was in one library, and that got smoked out, and that was the end of that knowledge. It would be, good, hurry up, we should make copies. Okay, so we have all this dust, you see, little pieces of dust that all have copies of it all over, and they can't get rid of all the dust, you see. Anyway, that's what it amounts to. Now you might ask, if we had something that small, the 5 atoms on a side is a little, well, you could still read that. Yeah, but let's go back to the 20,000 times reduced encyclopedia, which isn't as small as you can get, but pretty dramatic and good enough, right? How can you read it? Well, if you try an ordinary microscope to look at it, you can't magnify more than 2,000 times, because light has a structure, and you can't see any closer than the structure, called the wavelength of light. But you can use electron microscopes, which don't stop at 2,000, go up to 200,000. Well, we only need 20,000. It's only 10 times better than light. It's rather easy, actually, to see 20,000 times reduced pictures with an electron microscope. It would be very easy to read this book that we wrote on the head of the pin, or this encyclopedia, with an electron microscope. The next question is, how would we write it? Well, it's possible to write it someday by using a kind of a thing like an electron microscope in reverse, in which to take the large-scale writing and use the lenses backwards to control a beam, which is so fine, which is very fine, instead of running the microscope. You know, you can run a telescope backwards, you look through the wrong end, you've probably done this, and everything looks small. You can do the same with a microscope, and you can do that with an electron microscope. So you can make the pictures very tiny and imprint them easily, not very easily. This turns out at the present time to be very difficult at the moment. That reverse electron microscope has not been developed very far, but I'm going to tell you what the situation is today. The first time I ever gave this part of the speech was 20 years ago, and you just said that someday, I'm surprised we haven't done it yet, and someday it'll be done. Now I can show that it can be done. But before I do that, I would like to talk about what we are now actually doing commercially in making things. How small do we make things? How delicately can we make them? Are we writing the Lord's Prayer on the head of a pin? No, we're not actually writing the Lord's Prayer on the head of a pin. We're doing a much smaller scale than that, but we're not writing the Lord's Prayer, because in the meantime, interests have changed somewhat. And I'll show you on the first slide, if it's available, please, something that you've all heard of, which is a computer chip, which is made, what happened to the slide? Oh, I see. Okay. This is only 20,000 times reduced, and it's very difficult to see it because it's so fine. That's it, good. And it has to be focused. It's really quite difficult to see that there's a very fine structure, and you can see some of the structure, but you can't quite see how fine it really is. This whole thing is about 3 millimeters across, and you've seen these things in magazines, and you say, well, it's just computers and so on. But from the point of view of humankind and its development, it's really quite an achievement to be able to manufacture something with such fineness of detail. The patterns look rather beautiful when they're worked out, and it does appear as an artistic thing too. But the beautiful thing about this is the delightfully accurate workmanship. We're always talking about workmanship. They don't do anything like we used to do. We used to polish things down. The accuracy which they polish things is less than one of these little notches in here. Now we can even make something in that much detail. And it's made and used as is an example of a computer chip. I'm sorry to bother you to put the lights back again, but it'll be a minute or two before I get to the next slide. Okay? It's a kind of a complicated arrangement. Because I wanted to explain how such a thing is made. This is made, that was magnified about 20,000 times. We can make things at 2,000 times, I mean. That was 2,000 times. 20,000 times is very much harder because 2,000 times we can use light. And the way it's done is to use a lens system, a microscope, backwards. What we do is you take some material, in fact in this particular case it's silicon, and there's a layer of very beautifully made, very pure silicon. The reason is any piece of dirt or scratch or anything that's wrong with it is a great big monster boulder at this scale, and you don't want any dirt, so you get very pure silicon. And then in a vacuum you let in oxygen, and then what forms on the surface of this is a layer of a compound silicon dioxide, which is simply quartz or sand or like glass. It's a thin layer of glass which is an insulator. Silicon is a conductor. So we're going to build this thing up. Now on top of this, the next layer, we put on some, oh, I got lots of colors, that's great. Another chemical which is evaporated on in the thin layer, which is called a photoresist. And then light is shown on here. Light comes down. Let's say like this, in a pattern. No light here, and only light here and here because it's an optical system. It's a picture. In other words, a picture is projected, a black and white picture is shown on here. And what happens to the light, what the light does, is make this material resist etching later. Or rather, dissolving it off, excuse me. So it gets to be resistant here, where the light's shown. I've got a simple pattern, but you might have a little section in here and so forth. So you can make the shapes that you want by using the light backwards to make this thing so that it doesn't dissolve. And then what happens, you dissolve this material away, right? And just have these. Then you attack the silicon dioxide, the glass, with hydrofluoric acid, which dissolves glass, and this part is erased so that this disappears. Let's say the silicon dioxide is white and, brown. So brown. And so we get things like this, you see, little columns of brown on top of the silicon, right? And then the red stuff that I showed there is dissolved by another chemical because it was only a tool and a scaffolding, and so we get to this picture. Remember that these are insulators, and this is a conductor. So the next step is to evaporate some silicon again and to make a contact. It goes on, and I'm not going to go on and on. But the next level is, say, silicon or transistor material, which is silicon with something dissolved in it, let's say is laid down here in a layer all over, filling all this. But then, again, with a resist and so forth, pieces of it are dissolved away so they can get little caps and so on, and make more insulator in various layers, each time deciding where the stuff goes by using this photoresist trick. And they're ultimately building up, say, a metal connector, finally, with a similar device, the same general idea. Let's say metal is put across from here to here. So now we have two transistors connected together. And that slide that I showed the result, looking down on this, of such a work of art and commercial effort, industry, to manufacture a particular design of an electric circuit. It's an enormously complicated electric circuit. They can make calculations all by itself. But the design, the thing that determines the pattern, is the original arrangement of light. And I just wanted to show you how it is made. But that's only 2,000 times. And we want to now talk about 20,000 times, small. And that is new and different. It hasn't been made yet. Because we can't do it, because light can only go down 2,000 times. So we have to do it some other way if we're ever going to do it. I spoke about writing at 20,000 times reduced. And what I want to show you now is writing 20,000 times reduced. This is a non-commercial process. This is a process that is being worked out in the frontiers of this business, trying to see how small we can make things and how small we can write things. And there's a particular example. There's a laboratory at Cornell that makes these, that's doing this particular research, micro something or other laboratory, right? Very small, making things very small. And I have a friend, Tom Von Sant, who's an artist who loves art and science and commerce and everything else together. He's a real man of the present era and not one artist who sneers at science and doesn't understand the world he's in. He loves the world he's in and he loves art. And so it was asked them if they would make a drawing for him. He designed the drawing, and he made a drawing, which is the smallest drawing ever made by anybody in the world. Okay? And in the next slide, I want to show you the smallest drawing in the world. Okay? This is supposed to be a drawing of an eye. It's an artistic work. Okay? What it really is was a salt crystal and a beam that was moved around to make hole, to dig away the salt so as to make this image. And then the image is looked at in an electron microscope. This thing, compared to the normal human eye, is 100,000 times reduced. That's more than I've been talking about before. 100,000 times smaller than the human eye is the actual drawing. And of course, this is a magnification back again so you can see it. The artist, of course, has the right quality. All art has this quality of a kind of, you don't really care. It's sort of, you know, it's very beautiful. This was caused by a truck that came by, shaking the beam, you know, shaking the apparatus, because even the tiniest vibration at this scale is a big movement, and that produced that, which makes a very beautiful picture. To get some idea of the scale of this, the distance across this thing is approximately 100 atoms, which is as small as anything has been made yet. Tom had a definite idea. He wanted 100,000 times less than an eye for a reason that you'll understand in a moment. And people there were disappointed because they can make the dot about half as big and the lines about half as thick and the whole drawing about half size. But Tom insisted that this be the size. Because he had another drawing of an eye, which I would like to show you, the same artist had previously made another drawing of an eye, which is in the next slide. And that, of course, is the true kind of art with different kinds of patches at different colors and so on, which represents modern art, right? That's a beautiful picture of an eye. I really, you know, if you made an eye, you'd make a circle and a line, but they make it with such beautiful colors and everything else. To see more about this picture, I want to show it at a different scale, which is in the next slide, because he has included here the eyebrows of the eye, and something rings under the eye, you see, and there's the eye. To get still a better idea of the true scale of the canvas for this picture, we look at the next slide. This is the city of Los Angeles, and there is the eye. And this is the largest picture in the world that has ever been drawn. Okay? And it is 100,000 times larger than a normal eye. Now I would like to tell you a little bit about how the picture was made. How did that make? This, of course, is a picture from a Landsat satellite. This drawing's so big you can't just look at it. You've got to go up there 600 miles into the sky and look down with a Landsat satellite to see it. Is it possible to go backwards with the slides to 2 slides back from this? Yes, thank you. What was actually done is what happens with the Landsat satellite is this. It has a beam and it looks at the ground, goes back and forth like this as it sails over the ground, and the beam goes back and forth, and it's computed, the light that comes at any moment into the cell, moment after moment, is computed, and an image, a spot, a little square is made for that direction at that moment. There are 3 different colors information that's taken in and that's added together to get the color. Each one of these is called a pixel because it's all calculated from the thing, and you don't see that when you look at the full picture. Just like when you look at a complete picture in a magazine, you know it's made of a lot tiny dots. Well, the dots, they're too small to see in the normal picture, but here they are big enough to see. Now, each one of these covers about an acre. And we would like to know how Tom von Sant had the energy to cover all these acres with white over a distance of 2.5 kilometers. This picture corresponds to a drawing 2.5 kilometers wide. And this is the way he did it. He set up a mirror at different stations. There are 24 mirrors in this picture. Each mirror is set somewhere, and the angle exactly calculated, because the timing for the Landsat was well known, was given to him by the Landsat people, and he calculated the angle to set a mirror so that at the moment that the beam went to look at that acre, the angle was just right that the sun went right up into the camera and, you know, saturated the camera. It was a flash of white so that that particular pixel looked like the whole thing was white. It's just as though, you see, you don't have to have a whole acre. So he had 24 mirrors set up in the desert, each one calculated very accurately. Could you just see that just one moment? Can I see the picture just one moment? Because there's one slight error in it, which I want to call your attention to. This pixel didn't come out quite right. There's an error there. Now I come to the next slide. I mean the final slide, the 7th one. Yeah, that's right. That shows them setting up. This is Tom von Sant. And there he is with the angles, you see, and the levels and everything else, setting up his mirror to the correct angle in order to reflect the light into the Landsat in order to produce this picture for us. What happened was, it turned out, after he saw the picture and he went back to discover what happened, a jackrabbit had run over the mirror and changed the angle, so it didn't work. I know that's not got to do with small things, it has to do with large things. But I couldn't resist, after I showed you the smallest drawing ever made, to show you that the same artist has also made the largest drawing ever made. And the comparison between the eye of the child and this eye can be seen something like this. If you think of the eyelash, which is a hair on the ordinary eye, and magnify that hair until it's about the size of an eye, then an eye gets to be across this room. Then you're halfway there. Then you take an eyelash of that eye and magnify it until it's across this room, and the big eye is 2.5 kilometers. Another way of expressing the size is to say, let us go up another scale of the same amount again, of another 100,000. And try to draw an eye. Where would we have to draw it? What is it? 100,000 times bigger than the 2.5 kilometer eye. It turns out is a beautiful eye in the heavens, namely Saturn with her rings. So that gives you some idea of the enormous scale, both up and all the way down, how tiny that drawing actually is. As 2.5 kilometers is to your eye, so that your eye is to that original first drawing, which is so very tiny. The next question is, what about making computers still smaller? And now I launch onto another thing. Not a question of what's practical today, but what's in principle practical. It's already noticed, for instance, that if we were to try to make the wires about half as big or a third as big as the wires in that particular design, it's a strange thing that when wires carry electricity too long, they move, the matter moves. It doesn't move much. It doesn't make any difference there, but when the wires are very much thinner, it tears the wires apart. So you have a problem with wires, and everybody's worrying about that. But that's like the sound barrier. You may be all too young to have heard of the sound barrier, but there was once a time when it was said that no airplane can travel faster than the speed of sound. And the reason was, of course, that airplanes were designed considering, assuming that the air is essentially not very compressible. It's not easy to squeeze it into a small space because the airplanes went slow enough that there wasn't much force to squeeze it into a small space, so it always expanded. It was always not squeezed. And the theory and the analysis and the experiments all dealt with air that was not compressed. It was then realized that if you took into account the compression, that airplane wouldn't work with its propeller, and everything wouldn't work. The propeller would go too fast and it wouldn't pull. So there was a barrier. How are we going to go faster than the speed of sound? It just means there's no law of physics that says that you can't go faster than the speed of sound. It just requires a completely different design. So these limitations that you hear about mean only that you can't go on with the same design, but it doesn't mean that it's not possible in principle. And therefore I have considered the question, never mind about making it with wires. Let's make it a different way, make computers a different way, with atoms, with interactions, with certain kinds of connections. How small can it be made? Can it be made so that each one atom, in the state of one atom, tells you yes or no instead of gold and silver? And the answer is, of course, that the laws of physics that you have to use are very different than the laws here. They're called quantum mechanical laws. The scale is so small. We have to worry about the uncertainty principle and everything else. But just let me tell you that it turns out to be possible, according to the laws of physics in principle, to build a computer in which each bit or each little piece of information is one atom large. And there's no problem in that. And it was something I had some fun working out. But I said that this talk was about machines. And of course a computer is a kind of machine. But the machine you usually think of when you think of machines is machines with movable parts. Now let us talk about the possibility of making machines of movable parts which are very tiny. The immediate look in all the faces, what for? Mental entertainment. Maybe someday they'll find a use for it, okay? How small can we make machines? It's just thinking for the fun of it, okay? You don't worry about it that hasn't any application. It doesn't cost you anything not to have an application. It's just fun. Okay, so we're not going to worry about how we use these dumb things. We're just going to try to make them. How could we make movable matter, little machines, tiny machines that would operate that are very, very small? You see, today we have great big hands, and they're this fat and lumpy, and we can make tiny little watches. But that's nothing compared, I don't mean a computer watch, because that's not got moving parts, but a machine with moving parts inside that is extremely small. Now, how can we do that? One way that has been suggested is this. You know that the radioactive plants and so on have to manipulate bottles and turn nuts and so forth, and they have slave hands which are operated through electrical connections with bigger hands. You move these levers and it controls the hands on the other end of the wire. Well, there's no reason why the hands on the other end of the wire, that is wrenches and whatever they are, you know, they're operated from out here, need to be the same size as the thing. So you have the wires run to control very tiny wrenches to make small things. And what do you make with that? You make another pair of hands that are still smaller. So that now you can reconnect your wires to a smaller set of hands in which you work for a while manufacturing things at a smaller scale, and then with those making things at a smaller scale and so on. Of course, when you got all through with this, you'd say, you've only got one pair of hands to make one tiny little machine. But actually, the right way to do it, naturally, is that when you made the first pair, you make two pair, and then they make two pair, and they make two pairs. So you have really thousands and thousands and thousands of very tiny pairs, all following the same wires and manufacturing small devices, machinery and otherwise. That's one way that's been suggested. That was probably not a very practical way. People had tried a little bit, but it didn't go very far. But how about using this scheme? How? It's all solid. Well, why does it have to be all solid? Why can't we do the same layer scheme and put in a piece, I'm not going to go into the details of laying down the different layers, but it's the same idea. You have the silicon, and then you have some other substance, perhaps not silicon oxide this time. Let's say a substance we'll call blue, of this shape, let's say. It's no harm in manufacturing. There's a piece of silicon in here. I guess I should fill out the blue. There's a piece of silicon in here. And perhaps, just to make it interesting, silicon dioxide. I was brown last time, so to keep the things more or less similar. Other substances here, insulators or conductors. And other layers. Let's simplify it. You can make all kinds of things, but something like that. And then there's the blue material here. But the blue material is a substance that's easily dissolved away, but not the brown. And if you dissolve it away, that's a loose piece. Okay? Now, these things are electrical. They have all kinds of wiring. You can bring electrical voltages and stuff all over these devices by using the other technique. So you could put electrical voltages on the sides and move this back and forth with an electrical charge. So you can move things around. Now, we've never done anything like that, but it's possible to make devices in which we have loose pieces. That's another way of making. That's a very simple, elementary fact that we can move one piece. You say, that's nothing. Yeah, no, it's nothing, but with a little more imagination, you put a sequence of pieces or a sequence of poles and move it in succession from place to place and carry objects over the surface of the silicon, like cars and so on. It's kind of fun. I haven't got the time to follow the amusing time I had working on all these things, but you can start out and find out that you can move things about with electrical devices and so forth. And therefore, the second way of manufacturing small machines would be the evaporate and etch, freeing pieces of object, etc. You can move them with electrical forces, for example. And what would the uses be? I told you I wasn't going to consider it, but just for fun, the first use of this thing would be to make an optical shutter. You could have this thing over a hole, and when you move it, the hole opens. They're very, very tiny, and they're all over an area. That's a light control. You can make pictures because you have electrical control of which ones you open and which ones you shut. You say, oh, we can already make pictures, but we can make very powerful pictures. That is, TV pictures are projected only in a small box. A big projection is rather poor because you can shine the light and it's kind of too weak for the fluorescent screens. But you can shine a strong light directly through this thing because there's nothing but shutters, and open them and close them in different places and make pictures move and so on with electrical control. Sir?
What I'm confused about is you said that something can only be magnified to 2,000 times and then
Optically, with optics.
an impact problem. If you could reduce the light, as you're talking about small shutters or small cameras, would it be possible then?
No, you can't make light any smaller than the size of the wavelength of light. These pictures that I showed you of were with an electron microscope, which can go to a smaller scale. I'm back here at the scale 2000. I should have been more clear. It's much smaller than any machine has ever been made, let me assure you already, very much. But this would still be at the scale of light, and it would open and close holes that light could go through. Yes. I am not talking about making it smaller than that. I mean, we haven't done anything like that.
Magnetize it, make it a generator?
You could think of doing things like that, yes. The question is other uses of the stuff. I've thought of a few things. The present way of manufacturing these things and putting different substances in different places is a long and tedious thing. The workmanship needed to get those second pictures to be at the right place relative to the first ones and so on. It's a hell of a job. Suppose instead we could squirt the stuff where we wanted it. How? By having a big flat framework with a whole lot of nozzles with movable holes with the chemicals coming through. But you have to have a valve. You have to move something. So we make it out of this kind of stuff once, you see. Then we bring it up and goes, and now we have all of the stuff in the right place. Then, of course, there's no limit on the scale. Light is not involved anymore, and we can gradually make things smaller. So there's another direction. Another thing is to imitate a large number of important chemical reactions and biological reactions. We have membranes with special enzymes or special molecules in special places. They act like special catalysts. They control reactions very delicately, the kind of delicate control that's in the human body or in any living thing. And these controls, we're beginning to understand how they're made. They're layers of membrane in which these protein molecules have been set in certain particular places. But the scale is so tiny compared to where we are, and we can't think to manufacture them directly and put the stuff exactly where we want. We maybe try by putting something, and maybe it lands in the right place, and by some technique or other, we can make a membrane or another about right. But we can't make all the variety and all the different possibilities for different types of reactions by simply placing the enzymes into the layers where we want them. But we need tools. We need tiny tools to push things around, to make things go. As a matter of fact, if you went to the full limit, we wouldn't need chemists anymore. All that a chemist does is make a new molecule with a different arrangement of atoms. So if you went down to a small enough scale, you just put the atoms down where you want them to make the molecule. No hocus pocus with bottles and colored liquids. Actually, that's really magical how they do that. Well, other things have been thought of, the question of making a piece of machinery not that's connected like this in a hole, but a free, swimming, mechanical thing, you see. Naturally, the first application for things, just like it was for computers that would be most popular, would be games. And the game this time is that you have this little thing that goes, you have a control from the outside, it's electrically sensitive, and you can, or send it signals. And it has a kind of sword, see, and it fights paramecia. You watch under the microscope, and you have this thing, and you control it, and you're fighting the paramecia, see, with your little device. A friend of mine named Al Hibbs suggested something else that's going to shock you, and the idea is to swallow the surgeon. The surgeon is a machine with knives that's very tiny that can go down around and be controlled and go into the blood vessels and down in here and carve away the plaque or whatever heck it has to do and come, okay? You yes, fantastic boy. You swallow the surgeon, yes.
Fantastic.
Well, I'm a little late with my idea, but the problem is that I manufactured this. Hibbs gave me the idea 20 years ago, and this is a rather, in some respects, an old talk. But not in all the respects because of these new pictures. I would like just to finish this off, though, to say that there's quite a considerable amount of things that you have to think about if you try to make machines smaller, because it isn't merely a matter, like you say, of magnetically making the same thing smaller. You take an electric motor and made every part smaller, it won't work. Various things that come out in different proportions, you see, like the weight and the strength and the air resistance and everything. Ordinary thing like electrical resistance in another scale is enormously too high relative and makes a serious problem. But we know how to get around that with superconductors, and again, the trick, other design. When some proportions get enough different so that it's impossible to use the old design, then you can use some other thing that's bigger to make a new design, just like we did with jet planes. There's no real barrier. But I would like to explain the idea that scale doesn't really work very well by imagining a rather silly thing to try to do, is to make a very tiny internal combustion engine. Very, very tiny. Because it works, the internal combustion engine works like this. You have a cylinder and a, spark plug. And the gas goes in, the spark plug goes off. Nothing wrong with making a smaller spark plug, that's all right. The gasoline explodes, it gives a lot of heat, and the heat expands the gas, pushes the piston, and then something happens or other, and there you go, okay? Now, some of the heat of the gasoline is lost by heating up the walls of the cylinder. You know that because you have to cool the engine. I mean, it gets warm. But it's rather an insufficient, not very significant amount of the heat. Most of the heat is still used to expand the gas. Now, if we made the thing, let us say, 10 times smaller, you still would work actually, but you get the idea from 10. We want to make it 100 times smaller, you'll see it's absolutely hopeless. Let's take 10 times smaller. Then, because the cylinder is 10 times shorter, 10 times narrow, and 10 times each way, the volume in the cylinder, the amount of gas that you made, is 1,000 times smaller. The heat that's been generated is 1,000 times smaller. But the surface of the cylinder to where the heat loss is going to go, if after a little bit you'll see, is only 100 times smaller. It's square inches. And if you contract just 2 ways to make the surface smaller, it's only 100 times smaller. So you have 1,000 times less heat for 100 times less surface. That is to say, the surface relative to the volume that you're heating is 10 times more. It leaks faster, 10 times faster into the casing. And if you try to think of making the machine 100 times smaller, which is really not a very tiny machine from the point of view that I'm taking, of really weensy machines, you see that it's hopeless. As soon as you would explode this infinitesimal amount of gasoline in this tiny, tiny cavity, then the heat of it wouldn't be, before it had any chance to push anything, it would leak out immediately into the container. So you have to redesign. Turns out, following the laws of physics. There's nothing against it in principle. Every time I mention this, somebody always pulls up some difficulty about electrical resistance or something like this. The most interesting one is when I talked about the object that was sailing along in the water, right? Moving through fluids is entirely different. Things like resistance, it turns out, if you look in proportion, is different. If I were to take a very tiny thing in water and expand it to our dimensions, the analogous situation is that it's swimming in extremely thick honey. And the ordinary ways of flapping, let's say a fish, you want to make a tiny fish, of flapping the fins and so on to push it nicely through the water by the inertia of the water, doesn't work because they're just ick in the icky stuff, okay? And the fish is stuck in the goo. But how do I know then that I can make very tiny machines, that it's possible according to the laws of physics? Because I'm a physicist and I check the laws of physics and it's okay, I'm telling you. But I got another way to tell you. Living things have already done it. Bacteria swim. They swim through the water at the scale that corresponds to thick goop. And how do they do it? It would be analogous to the following. You have a kind of a corkscrew, a piece of iron or something. This is more magnified. Inside a sleeve, like a leather sleeve or a rubber sleeve. And you simply turn this thing. Okay, so the corkscrew turns inside the sleeve. You've got to picture this. You see, the sleeve is there. So this corkscrew is turning, the surface is the same, and it screws its way through the fluid. The flagella of a bacterium is built that way. It's a corkscrew of a piece on the inside, which is solid, which turns, and the motion that's produced by this is really like working with a corkscrew going through the stuff. You're pulling yourself forward. It's as if you were in sufficiently tough, like cork. You want to move through cork. Well, you take a corkscrew and go and push, you know, of course the cork's got to give a little because it's not cork, it's slightly thick honey. So you keep going and pull yourself forward. The only problem is what happens to the corkscrew. That's the trick of having the solid thing inside of the sleeve so that you can carry it along with you. It doesn't get lost in the back. And that's the way a bacterium moves, by a completely different scheme. That scheme is utterly inefficient in real water. Turning this corkscrew would have very little effect unless you turned it very fast to get some inertial resistance, which is better to flap a flap, like the fins of a fish, you see. So when you allow for the fact that when you go to different scales, different things at different proportions become important, you have a delightful time in redesigning all kinds of familiar machinery to see if you can do it. And give or take 25, 30 years, there'll be some practical use for this. What it is, I don't know. And maybe in 20 or 30 years, I'll think about that and give you another lecture on how these damn things could be used. Thanks very much. Yeah, I can answer.
Well, you could.
Okay. Have any questions? Yes?
Does that, you mentioned that when you go very small in scale, the liquid becomes very viscous. Does that imply that if you could build a very large being, it could move through the air in the same way? And that the air would then become thick enough to support it? If you up the scale...
You have big airplanes that work fine.
Yeah, I know, but supposing you upped it 10,000 times or something with the air...
Nothing much happens because already the resistance of the air, I mean, it's a dynamic resistance now. The ickiness of air, what we call a viscosity, the analog of the honey, is long since very unimportant. The motions that you produce with air propellers and so on start a flow, which it's true that the last motions as it dies out has something to do with the viscosity. But the initial motions are the ones that are important. They're dynamic. The airplane goes by the inertia of pushing air down, not anything to do with resistance, you see, by thickness. It's just the mass that moves, that's pushed down by the wing as it goes through. And the recoil from the air going down holds the plane up. And that would be just as good for a larger plane. However, it is true that if you took the same kind of an airplane and simply increased it by 100 times, it won't fly. The reason this time is that weight has increased as the cube, and the lifting power from the area of the wings only by the square, you know, the same thing backwards. So you have to have it hollow. Notice our big airplanes are hollow. Because the weight, if the airplane really had the corresponding weight as you increase the size, it would get more and more difficult to make it fly. This goes like that. I mean, everything that you think of, this changes and that changes, and it's true that at different scales, different things are important.
So at 10,000 times as big, the air does not become viscous.
No, the air doesn't become viscous. No, it's going the wrong way. Viscous, you got to get effective viscosity goes going for smaller skies. Yes, sir.
Well, let's see if I can phrase this right. You're an original thinker. I would like to ask you, how would you go about designing maybe a miniature, somewhat smaller but grand coulee, an anti-gravity machine
I can't.
that you could use for...
No, I can't. I don't know how to make any anti-gravity machine.
You would make the world's problem.
It doesn't make any difference. I still don't know how to do it. What the game I play is a very interesting one. It's imagination in a tight straitjacket, which is this, that it has to agree with the known laws of physics. I'm not going to assume that maybe the laws of physics have changed, then I can design something. But I try, supposing it's everything that we know is true as we think it is, as if we do. If we're wrong, of course, we can redesign something with the new laws later. But the game is to try to figure out, with what we know, what's possible. So it requires imagination to think of what's possible. And then it requires an analysis back, a checking, to see whether it fits, it's allowed according to what is known, okay? And in the case of an anti-gravity machine, I immediately give up because my understanding of the laws of gravity are such that I don't see any way, it doesn't make sense for anti-gravity, okay? The only anti-gravity machine, that is things which oppose gravity, which are very effective, are things like you're using now, a pillow or a floor under your behind. That is an anti-gravity machine, and it will support you in space above the Earth, a few feet in this case, for reasonably unlimited time. Yes?
How absolute are the known laws of physics?
They always, we find more things all the time, and there are things that are not known. So there's an edge that's unknown, and there's a certain amount of behavior that's been studied over and over in a certain realm. You see, there are variables that change, like the size or the dimensions or something like that. When you get too far too small, if I start to talk about distances that are 1,000,000 times 1,000,000 times 1,000,000 times 1,000,000 times smaller than a centimeter, then I don't know what the right laws are, okay? But in the realm of a few centimeters, for example, in ordinary behavior, they're pretty well gone over it. There doesn't seem to be anything wrong with them. And the laws that I need for the scales that I've been using, down to atomic scales and so on, are in extremely good control. It's not very likely that I'm making any mistake there, okay? In the realm that I've been talking about in this lecture. If I were talking about much smaller than that, then I would be more humble. Yes?
One from way back when you early started that was nagging
you're
me
way
then.
behind.
Oh, I know. I'm slow, you know.
Yes?
It's about making things with parts that are 1 atom big, or
Yes.
even 5 atoms big.
Yes.
I
used 100 atoms.
until you said you were not going to break the laws of physics, I
Yes.
wasn't going to heckle you about this, but it has been concerning me from then
Why?
till now, how you're going to make these atoms stand still, or do
They
they
don't
just
stand-
do that?
The atoms don't stand still. At an ordinary temperature, they're always jiggling. But if you take a substance like gold or silver, the forces between them is rather strong, and they stay next to each other. They just jiggle in place. Atoms which jiggle in place are solids. Things that are solid are made of atoms which, although they're jiggling, they never get out of place. If you took one away, the other's in the right place. It pulls them back. You see, it's a perpetual check with your friend. You okay? Yes, I'm okay. It's like the people marching in a... It's like the high school band march, okay? Nobody really knows what to do. They're going like this, and it's okay, it holds together, okay? But if there's too much jiggling, and too many people are out, you can imagine if this line gets broken up because he looks at him and he's far out, and so he tries to get out and he gets, and so it all tumbles around each other. So if you make too much temperature or use a substance where the forces are too weak, they roll over and they lose the strength, and that's a liquid. Okay, so I don't want to make this out of liquid. I said gold and silver, and I meant ordinary temperatures, and that's why I used though 5 atoms in a lump, because if I had used only 5 by 5 by 5 was 100 atoms. If I'd used only about 5 atoms, the jiggling would from time to time by accident let one atom move away and would get lost, and then another and another, and after some years I would have lost the description of the human race's knowledge. And now I want the seed to last longer, so I figured 5 atoms and calculated that the time for that is billions of years before that gets disturbed by these jigglings. Sir? Oh.
Does the lasers give you a chance to work it that small?
No, the lasers are light, and they are used in these devices because they're accurate light. They're very helpful in controlling the light and focusing and everything else, but they can't get any smaller than a scale of about 2,000 reduction, because the light wavelength, there's a wave of light is that big. I mean, it's millionths of an inch, but they can't get any smaller than that scale. Light has a scale, and you can't, it's like using chopsticks, right? To pick up something. Well, it's not very good because you can still make it with chopsticks because they have sharp edges, so I haven't got a very good analog yet, but it's using some kind of blobs to pick something up that are much bigger than the thing you're trying to pick up, and you can't do it. Yes, sir?
One thing that's always fascinated me, kind of brought it up today, is the fact that at one point in time, man didn't know what would happen if we went faster than the speed of sound.
Yes.
And obviously, we designed something and got there.
Yes.
Well, the human eye can really only detect light.
That's true.
When we know the speed of
When
light.
it's using in the ordinary way.
In the ordinary
It also can detect the sock in the jaw, the sock on the side of the head as a flash too, but the normal uses were light.
Now my question is, does the law of physics include the fact that matter can actually go faster than the speed of light?
No. No, any object which is going slow according to the present laws of physics and relativity, any object which is now going less than the speed of light cannot be accelerated beyond the speed of light. If you keep on pushing it harder and harder, using up more and more energy to give it energy, it goes faster and faster and faster, but what happens is it gets heavier. So to give it a little bit more speed, it's more inertia, right? So it's harder and harder, and you put more and more energy, it just gets heavier and heavier, and gets closer and closer and closer, but never quite gets to the speed of light, and certainly never surpasses it. In the machines in which we accelerate electrons, for instance, and to go around like in SLAC here or wherever, we get them going so that the mass, we've put so much energy in, that they come to something like I've been doing this quick so my number may be slightly off, 160 billionth, that may be slightly off, of the speed of light. In other words, it's not the speed of light, it's short by about 160 millionth, okay? Sorry, 160 millionth of the speed of light, and 1,600 million. Never mind, very small fraction. It's very close. And the mass of these things has gotten to 40,000 times the mass they have when they're standing still. An electron becomes 20 times heavier than a proton. Right?
What about antimatter? When you're dealing with antimatter, wouldn't it appear, and what I bring the question up, is because this is a likely community to bring this up, is the fact that in the spiritual world, which a lot of people delve in, it's possible that things exist and live beyond our ability to see them.
Yes.
And if this be the case, is it possible that they are vibrating at speeds which are greater than the speed of light, therefore have a different law?
The only thing I can tell you are the things that I can make observations about. If you ask me questions about something that I cannot see with any instruments whatsoever, they can be doing anything, whatever. I have no way to tell. You can have what you want. As long as I can't see it with any instrument, okay? As long as I can't see it with any instrument. But if you give me one clue way in, you see, I can make some tests and I'll be able to answer your question. Otherwise, I'm empty-minded.
That's why I suggest antimatter, because
No, we know all about antimatter. We see it in the laboratory. We do experiments with it. There's nothing spiritual about it. I mean, excuse me. Because the whole world might be completely spiritual and all that stuff. That's fine. But it's the same kind of stuff as matter. It's just as available to experiment. We know a large amount about the laws of the way it behaves.
Does it vibrate? Is it substance?
Yes, it's substance in the same way that any other substance is. I mean, normal matter is substance. And whether normal matter vibrates or not is something we'd have to discuss what circumstances. Of course, normal matter vibrates when you hit a bell with a hammer, it vibrates. Yes?
A small question my lady is asking me constantly. What makes the world work?
Isn't it nice that small questions are so easy to answer? And you have problems with your lady? Those are your problem. Not my problem. Is there any other? Yes, yes.
What's your next? If this is the area you're now doing research in, no.
No, I play. I sometimes do. This I've been doing over since about 1950, on and off. You know, I played on a beach one day. I began to think of how small a space I need to write a book. And I thought the way to do it in those days, an easy way, would be to evaporate layers one after the other across on a big area, and that's easy to do. And I had 5 atoms again for one bit and so forth, and found that the thickness I'd have to go was about 1 inch in order to write the whole information in the book. But it's a 1 inch square, and every inch is the same. So if I sliced that into wires, each one would be the same, and I have thousands and thousands of wires, a copy of the same book. And I was absolutely amazed that a book could be put on a wire 2 inches long. Nowadays, that's relatively easy, but at the time I was amazed. I went around to all the people on the beach and said, hey, listen, do you know it's possible? Didn't sell any bananas. Yes?
What would you say is the most difficult problem?
I'm sorry, I didn't finish, but I know. I work on and off, and so it's not real work. Sometimes I get interested in the small computer or the machine or some question about resistance or something. Excuse me.
What would you say is the most difficult problem in all of physics that you can visualize?
What, you ready to work on it? We have a very large number of problems in physics that are not this kind of problem. This is a game engineering problem because the sizes I've used are well within the realm where there's not much uncertainty. And there's technical problems of making it which are interesting, but not the most important problem in physics. If you mean by physics fundamental physics or the laws of physics, then the more important problems have to do with discovering the places where we don't know the laws, okay, which is a detailed thing which is outside of the subject, would take me some time to explain. I will be happy to do so at another occasion, sir. Okay? See, my group is a tough group. Yes, these are members, yes. I get one that's like pistons, you know, and if he's not, he'll think of something else. Yes.
At the end of your book, you mentioned
My book?
Your book.
Which of the various books?
The one you autographed for me.
Oh, well, that for me.
You mentioned that you thought there would come a time when the excitement of what was going on in physics would slow down because
Yes.
things had been discovered, and your analogy
It was at least a possibility.
tourists discovering an otherwise beautiful area, and it becomes less interesting and less nice
Yes.
as more people know. That book was written 20 years ago. Do you think that's happening?
No. Well, it's true that the experiments are going more slowly, and each experiment is more difficult than the one before, and information is coming in slower. Nevertheless, I made a mistake. I thought, therefore, that the theorists would have less to work on, and therefore they wouldn't be quite as interesting. But I didn't realize the propensity of human beings to speculate. And so, as a matter of fact, when less data comes in, more theorists are working with more crazy theories than before. And I hadn't contemplated that because in my day things were more vigorous. When we got a theory, we could check it. Nowadays, since the data comes in slower, we have much more fun making large amounts. I see everybody's getting ready. See them sneaking out there? So I think we should, let's do it this way. Let everybody who wants to go, and if someone wants to stay, I'll answer some more questions for them. But those who have something to do, because there are other interesting activities in this wonderful, wonderful place of Esalen. So I'll come back to it in a minute, but wait, let's the others leave who wish to leave, and then we'll come back to those who have some questions yet. Oh my God, so many questions. She had a question. I ought to answer hers first.
Well, it's something about the time that's coming when all the things are going to fit together and we're going to have all the answers and we won't need physicists.
We don't know whether that's true. It's possible, but we don't know if it's true. But see, either thing is possible. Either that we find all the laws, that is to say we find laws, and as we check and check and check, everything fits, everything fits, everything fits, and it looks like we're done, and maybe we would be. Or it's possible that the data comes in slow and slower, like when you fall asleep or something like that. Not really, it doesn't go slow. But people get tired of it. There's too many new things and they not have any application, and it's too far out, and it's too expensive, and the high priests who are involved in it are not supported it much, and there are less and less people doing it. That's another way that the fundamental physics can stop. But applied physics, like discussions of matters of this kind, will go much longer than that, because there's all kinds of applications of the laws we haven't thought of yet. We're talking about two things: finding new laws, that is discovering new things about nature, and the other is finding new ways to use what we know. The second one will go on much longer than the first, and I cannot envisage how it stops. But the first one I could imagine, either that we get the answers or that we don't get the answers, and we don't get the answers but we're frantic all forever, thousands of years, or we don't get the answers and we give up. Or we get the answers, and that's all obvious. I can't see any other possibilities. It's obvious some other possibility is what's going to happen. Yes?
You said, as the laws of physics, when you talked about the heat engine, and
yes,
because the cooling rate and
right. That's all at the scale that we know the laws.
Well, if you wanted to make a heat engine, yes, what other mechanism would you use? Because you've got to follow some sort of cycle.
Yes, but there are many cycles of magnetism, of magnetized, the nuclear magnetism, for example, in the atoms and so on. There's many other things. The heat is at random motion, but the random motion of what? It doesn't have to be the motion of molecules bouncing, like an ordinary heat in an engine, but it can be the heat of spin, that is magnets swishing up and down, although the atoms that they correspond to are staying in place, and so on. So there are different scales at which we can get the heat operating systems and reversible cycles, if you want. But I use the internal combustion engine to illustrate that a particular type of engine, internal or heat engine, is not necessarily the way to go. We might get a clue from living creatures which do get their power from chemical reactions, and you might call them heat engines or not. They are in a way, but actually, so it's hard to answer exactly. We don't know exactly what you want, but I don't need to follow any particular type of engine, you see. I use different combinations of the laws. Yes, sir. I put you down once. Let's see if we can do it again.
I wonder, the power to be in physics.
Power to be
in physics. We'll put a new original thinker to the stake and burn him alive because the earth is flat.
After all.
After all.
Well, I think not, but perhaps I'll be the guy that gets burnt because the earth is flat. I'll take the risk. Right.
I want to go back to something in this drawing that...
Yes.
That
wasn't clear? No, it wasn't very
the
clear.
one thing that I'm not clear about is at that scale.
Yes.
What is it that physically makes light impossible to be reduced any further?
Light. Light is like, let us consider ocean waves or something, okay? And imagine a large number of corks on the shore. And I want to move corks in a small space. And the only waves I'm allowed to use are this long. It's impossible to figure out how to get waves at this normal wavelength to focus any shorter than about this size. You can, by bringing the waves from different sizes from a much bigger dimension. Bring things in, focusing the waves, but you can't get them any shorter than this characteristic length of the waves. And so the sloshing on the shore will move corks over about this much area. It's impossible to pick one cork out with waves that are this long, no matter how you combine them, okay? Well, by taking different waves, yes, yes, indeed.
Because
now, but different waves are not called light. We call them ultraviolet light, or X-rays, for instance. X-rays are, in fact, exactly that. They're light, but with a shorter wavelength than normal light. Now, in principle, you could do, and people are trying to do, this kind of a thing in which the X-rays affect the resist. You're absolutely right. They have to go through other technique. The photographic technique for making the pictures can't be silver and so forth, but you do it a different way. And there's a lot of work. And X-rays is, in fact, one way that is being worked on in various laboratories to reduce the size of this. Yes, that's a good idea. I'm sorry I answered your question wrong before, saying there was a limitation because it was light. I was assuming it was light. Yeah, but it could be X-rays. Or ultraviolet light. That's going a little bit. Ultraviolet light about half size, okay? But beyond that, we call it super hot, far ultraviolet or X-rays. Then there's soft X-rays, hard X-rays, so on. The size is going down and down and down. And that size can get smaller than an atom. It can get way much, much smaller, the size of a nucleus. And then there's hard gamma rays and so on. It's all the same scale. But the other direction in scale of longer waves is called red light, infrared light, far infrared light, heat waves, radio wave or television transmission waves, and radio waves. There's all one enormous scale from one end to the other, which from a physics point of view properly is the same thing and should be called by the same name. If we call it light, you may get a mistake because you think you mean visible light, okay? We call it electromagnetic radiation, which is a great big word, but it's supposed to encompass this phenomenon, which can have a scale like the ocean waves. But depending on what the scale is, the normal name of the thing is different. It's radio waves, or one day...
harmonic.
Yes, a harmonic oscillation, slow for radio waves, faster for television waves, faster for heat waves, faster for... and very fast for red light, and even faster for blue light, and then ultraviolet, and so on. It's just the same damn thing along a whole scale from one enormous range. Okay? Yeah.
I'm confused about...
Again? I have such trouble with you. You're always confused.
How can you detect something that's smaller than atoms? What can we have to detect them with?
That takes a great deal of ingenuity. Let me explain to you how you might be able to do that. Suppose that you wanted to detect something smaller than tennis balls, and all you have is tennis balls. Okay? Now, if you hit a tennis ball against a tennis ball, it's unlikely to bounce directly back. Well, excuse me, that's too complicated. Suppose you throw tennis balls at a wall of these things that you want to test if they're smaller. Then by seeing that how many tennis balls come through and how many bounce back, you can see how big the targets are. If one tennis ball has to occupy an area size of a tennis ball. So if you had one tennis ball on the wall and you threw them at random at it, the number that would bounce back would be depending on the size of that ball. But if that wasn't a ball but a pin, you'd have to have better aim. Yeah, something like that. It's something like that. So we measure, that's one way of going down in size. Okay? Another way of going down in size is to discover some relationships. For example, one of the ways of making light is to let electrons hit something with a certain energy, hit a metal. As you increase the energy, when you can still measure this wavelength, because it's still bigger than an atom, you measure it and you find the wavelengths getting shorter as you increase the energy of the collision. Now, you get to a point where you can't measure directly anymore, but the way you understand the laws is you just use more energy, you'll get shorter wavelengths. And that's the way we go to very much shorter wavelengths. And then after we make measurements, everything fits together, and there's lots of internal checks and so on. It's not very easy to describe in a few words.
Smaller than an atom, not smaller than an electron. I guess.
Yes, smaller than, well, it's hard to say how big an electron is, but it'll be pretty damn much smaller than an atom. in the following sense. An atom, say, is the size of the room, okay? Then the nucleus of the atom is a tiny speck. It takes me a minute. 100,000th times smaller. 100,000 times smaller. So you have to think exactly. It's a little tiny dot, like a period in a sentence, which is much smaller. And that we can measure too. But today we have, by using this method of using high energy collisions, with the high energy corresponds to short wavelength, we can go down to 1,000th of the size of a nucleus, of the smallest nucleus. So we're down on the insides of protons and things at the moment. That's what your taxpayer money has been able to produce. Yes, ma'am?
Can you use sound the way you use light? Could those little arrows be sound?
They could in principle, but sound wavelengths are very long on this scale. These little things, and the distances I'm drawing there are millionths of an inch.
But are there new kinds of sound, like
Ultrasound.
and could you do the same sort of...
Yes, ultrasound is smaller and shorter, and you could, indeed, you're right. Yes, you could use this very super frequency sound, not ordinary sound, not sounds you can hear with the ear.
No, I don't... Yeah.
Supersonic. No, not
pictures
supersonic. Yes, you're right. I made a mistake. I'm sorry. Yes, not auditory sound, but you could do this with shortwave sound.
Worse? I mean, is there any...
It's so easy with the light, and to get at these small distances, it's rather difficult with the sound, because the sound is a wave in matter of motion. And the matter is disorganized, the matter is shaking all the time, and it's hard to keep organized waves going any distance. So it's kind of strong absorption when you get the such short wavelength. But it's not a bad idea, as a matter of fact, and something that ought to be considered more. Sound waves can be made short rather easily, and that's a nice idea. I'm going to think about it some more. No, I'm not fooling, because it's not so easy. See, to get to the dimension of X-rays is rather complicated, but to get sound that has the size for the X-rays is, if I'm not mistaken, not that difficult. Although I'm not sure, I have to check the numbers and stuff, okay? But it's not a bad idea. I think. Tomorrow I'll see it's a bad idea, but right now...
What happens to sound as you increase the frequencies and go up?
Goes up in pitch.
No, I mean way beyond that. To upper limits. Way beyond that. Way beyond.
It goes to the point where the wavelength is the distance between the atoms and the substance that's trying to carry the sound, and then the sound can't be a wave anymore.
And then what does it become?
It's no longer, you can't make sounds of any higher pitch. There's no
so it
such
just
a thing.
ceases.
There isn't any.
Okay.
Yeah. It's as though you, let's see if I can get an easy example. You have a whole lot of people standing in a row, and you want to make a wave this way. You tell this one to raise his hand, and when the other one sees that hand going up, to move his hand, and so on. That's the rule. Everybody looks at the other one. And so you can make a wave in which the hands go up in a succession along the stream, right? And there's a certain distance. It depends on how fast people respond to who's moving their hands up. You know what I mean? There's this like the Rockettes, only not when they're all doing it at the same time, but you get this wave that they like to make, you know, and one end does the next. So you see this wave of beautiful legs rising, okay, over a distance. But it's perfectly clear that if I would ask you how, with those Rockettes, can you make a wave where the distance between the ups and the downs is less than the distance between the Rockettes? Well, how can I answer? There is no such a way. You can make the ups and downs of the legs. You know, this leg is up and that one's down quicker than one Rockette difference. And so you can't make a sound wave where the vibration of the successive atoms is in a pattern, which is what a sound wave is. It's a pattern like the Rockettes, but in which each atom next to each other is any faster than opposite. There just isn't any way to describe it. So that's what I mean by there's no more sound. It doesn't mean anything anymore, okay? Just a moment, we'll get to you. Yes, sir.
You mentioned in the electron accelerators as it approaches a speed of
Very
light.
Close. Very close.
The mass increases in the electron. What is it still an electron or?
Oh yes, it's still an electron. Just an electron moving very close to the speed of light and has the correct properties for such an object.
Why does it get heavier?
You have to read about relativity.
Does the diameter increase?
There isn't a particular diameter for an electron, so until you define what you mean by the diameter of an electron, I would have a discussion, have to make a discussion. However, if you take an object that has an evident diameter, such as an atom, a complete atom, and accelerate it very fast, the diameter stays the same in the direction at right angles to the motion, but the object appears to be more and more flattened like an ellipsoid until it becomes almost like a disk as you get very close to the speed of light. I'm sure you know this about relativity. I'm not giving lectures to my idiosyncratic thinking class on relativity. I just want everybody to know that as an advertisement for next year. We're not discussing, but I can't keep them down, okay? I can't keep them down. So, do we have any other questions? Yes?
Sort of an interview type question.
Oh, an interview type question.
What would you say is the most exciting thing, if there is one thing that you have discovered or been thinking or playing with over your career?
Well, that's an accident of history and of a particular individual. That has got a profound sense. But nevertheless, it's not very easy to answer. It's exciting in the sense that the answer came quick, suddenly. It's not the most important discovery, but it's the one that was fun because, well, there were two like that, so it's a little hard. Well, it was guessing at the laws for the disintegration, what's called beta decay, the weak interaction laws. I didn't guess them right, but I guessed them much righter than they had been guessed before. And it was right for quite a while. And then it was improved by another generation of physicists in a more complete form. That was fun. And the other time, I've been working for 2 years trying to understand why liquid helium is helium when it's liquefied at sufficiently low temperature, flows without any resistance. There is no more viscosity. It just goes, if you have a long, thin crack, for example, if you take a glass rod and put a piece of platinum wire in it and seal it together, then when you lower the temperature, because of the change in expansion, there's an infinitesimal crack between the glass and the platinum wire. Then you can use this crack and connect two vessels of helium, one higher than the other, and they'll flow through like this, and they'll overshoot by coasting and then go back the other way. There's just absolutely no resistance to flow. Helium had also a large number of other properties that were strange and unusual, but we thought we had the correct laws of physics, which are in the form of what's called quantum mechanics. But exactly how the quantum mechanics behaved, the formulas would produce these results, was not at all clear. Because there were so many atoms involved that it was too hard to solve the equations directly, and it took a lot of imagination to see how the thing really worked. And I got a big thrill of that because that sort of came to me suddenly. I had the right idea, and I gave myself an argument which showed it was wrong because I supposed a certain curve was smooth. And I suddenly remembered that that curve isn't smooth because we have another experiment. And then it sort of went bang, everything was okay. Because I was in trouble. See, I had the idea, and I had talked myself, I couldn't see what was the matter because I had this wrong idea about a certain curve from experiment, and I forgot. And then I suddenly remembered this fact, which would have saved the explanation. So it was like suddenly discovering, it opened up suddenly. It's fun when it's sudden. And of course it's very exciting and delightful when something like that happens and you work for several years trying to understand something. Then all of a sudden it becomes sudden, all of a sudden it's clear, okay? Or it's not completely clear, but it's clear that you got the key, that the whole thing is now pouring out. I mean, everything is just roaring, and now you can do all kinds of things and look at the details and keep on going and so on, and hope that you don't get stuck, that you didn't make another mistake, which happens very often. I have been very often excited. My wife says all the time, I have a lady too. She says, I come down, I've gotten it, I got it, you know? I've heard it before. Wait till tomorrow. And she's almost always right. Almost always, and again and again and again. Wait till tomorrow. Where I find out that I made a mistake, you know. Okay?
The Russians discovered like tennis, you know. The Russians have already discovered it 200 years ago, like tennis.
Like tennis. Right. Okay. Help. Help. No, it was okay. Huh?